Today we discuss so-called equicontinuous families of functions. So it's a topic covered on pages beginning from page 154 through. So what this is all about? This is a continuation of the topic of uniform convergence. So we have a metric space. It is a complete metric space, usually compact, and we are interested in functions that map x to a real number, functions that are continuous and bounded. Then we have proved that, we have introduced the set called the C of x of such functions, and we have proved that there is a particular nice metric called the D supremum on this set that makes it into a complete metric space. Complete. So let me recall what D sup is. So first of all, you have the norm, the supremum norm of a function. This is just the supremum of the absolute value of x on the set capital X. And now D sup is just the norm of the difference of two functions. As usual, as we construct a distance from a norm, we take the norm of the difference. So here as well. So we have shown that this makes this set into complete metric space. So every Cauchy sequence of such functions has a limit in this set. So a continuous limit. So that's important, as opposed to limits with respect to other metrics we discussed. Right. So now the question is, to what extent the compactness of the original set influences the behavior of the set of functions. So in particular, is it true that from every countable family of bounded continuous functions you can extract a converging subsequence that converges to a particular function as k goes to infinity, or not? So in general, the answer is no. But if we in addition assume equicontinuity, then the answer is yes. Okay, so this is what equicontinuity is all about. Equicontinuity. Okay, so now before proceeding further, I would like to discuss an important special case when x is countable, because that's how we will approach the general case. All right. So as a preliminary lemma, we discuss the case when x is countable and Fn is a countable family of functions from x to r that are pointwise bounded. So for any xi in x, so there is a constant mxi that bounds the absolute value of all functions in this family. So under these assumptions, we will show that there exists a converging subsequence of functions. Converging can be interpreted in several ways. So for instance, we can say that in the supremum norm, the norm of the difference of two elements can be made less than epsilon for all k and l greater than certain n epsilon, right? Or another way of saying this is f and k of xi converges to f of xi for all xi in x. So in other words, this sequence of numbers is convergent for all xi. Alright, so how do we prove it? It is not so hard. It requires a bit of a trickery with this diagonalization argument, something like you have seen when we proved that the set of real numbers is uncountable. So here it goes like this. So first of all, you select a subsequence f1, 1, 1, f1, 2, f1, 3, and so on. So it's a subsequence in here such that f1k of x1 is convergent. Such a subsequence exists because fn of x1 is bounded in absolute value by m of x1. So it's an infinite set of numbers inside an interval, right? This thing. So therefore you can select a subsequence of functions like this. Alright, so now in this subsequence you can select a subsequence that would also converge on x2. So we call it f22, f21, f22, f23, f24, and so on. So yeah, let me repeat. So f k of x2 is convergent, and as well f2k of x1 is convergent because it is a convergent subsequence of this. Alright, so then you take x3. Now from this subsequence you select a converging subsequence f31, f32, f33, f34, and so on. So you go on like this. For xn you select from the previous row xn minus 1, you select subsequence fn1, fn2, and so on. So somewhere here you would have fnn, and so on. And you go on. So now the trick is to select to find a subsequence that will converge for all xi. So how do we do it? Well, here comes a bit of a magic. So what you do, you select the diagonal. And indeed, this is a subsequence, and moreover, no matter which row you choose, then what goes on this diagonal underneath this row is a convergent subsequence of this row. Okay, so it means that for this particular xi, this subsequence will converge. So this means that it will converge for all xi. So what we have shown that fkk of xi is convergent for all xi in x. Alright, so this completes the proof of this particular lemma. As the next thing to consider, we have so we're going to give an example of a subsequence of a sequence of functions from 0 to 1 to R, such that you cannot so there will be no subsequence that is convergent in supremum norm. Right, so how do you see it? So how do you construct such a thing? Right, so here is a trick. So you take fn of x equals x squared over x squared plus 1 minus nx squared. So, so what we have that for all x in x, it's the sequence fn of x converges to 0, right? Yeah, it is very easy to see. On the other hand, fn of 1 over n is 1. So you see some kind of discrepancy. Yeah, indeed, you can just check this by plugging this in, right? So you have. So this will be 0 and they cancel each other, so it will be constant one. So you see, so now if we suppose that you have a subsequence that is convergent in the supremum norm, it will not work, right? So this is, yeah, this is really not what you would like to have, because as a supremum you can always take x to be nk, to be 1 over nk, so you would have 1 here and something very small there, so there is no way of making it work for all epsilon greater than 1, no. So therefore there is no convergent in this metric subsequence here. Alright, so yeah, so we have to understand what kind of extra properties we need. Alright, so now let us present this missing link, this condition that is required from a sequence of continuous bounded functions on a metric space to have a convergent subsequence. So it turns out that this condition looks very much like the definition of continuity itself, except that there are no dependencies of delta on x, so it automatically means that Fn is uniformly continuous. But not only this, also delta does not depend upon n. So it is doubly uniformly continuous. So not only with respect to x there is no difference, but also with respect to a particular function you have no difference, right? So in other words, when you have an f of x somewhere here and epsilon ball around then you will hit this ball using a particular delta ball in the pre-image, and this happens irrespectively of x and n. So delta only depends upon epsilon and nothing else. Right. So this is the definition. And now let's look at that example we considered just a few minutes ago. So the example of Fn equals x squared over x squared plus 1 minus nx squared. It is easy to see that this particular family of function is not equicontinuous because of that x equals 1 over n playing a very special role for some of Fn, but not for all of them. So that's essentially what's happening, why it doesn't work. So this is not equicontinuous. Alright, so now what I would like to present is a theorem that shows that if you have a uniformly convergent function, if you have a uniformly convergent sequence of functions, then it is equicontinuous, given nature of assumptions. Alright, so more precisely we have the following. So we have x t compact and Fn uniformly convergent to F a sequence of functions in C of x. So then Fn is equicontinuous. Alright, so now let's prove this. Okay, so we're given epsilon greater than 0. Now we know that as Fn is uniformly convergent, there will be some capital N, so that in the supreme norm Fn minus F capital N is less than epsilon over 3 for all n greater than or equal to n. Alright, so this will take care of everything that that is kind of far enough, right? So now we have also functions fi fi for I from 1 to capital N, right? So they are uniformly continuous. So you have fi of x minus fi of y in absolute value less than epsilon for some delta and all x and y at the distance less than delta. So yeah, that's because epsilon over 3. So that's because fi's are uniformly continuous. Just because we assume that x is compact. So every continuous function on a compact set is uniformly continuous. So you have this holding. Alright, so now what we do, you add this you use this delta, so we have Fn of x minus Fn of y would be less than or equal to Fn of x minus F capital N of y. Sorry, x plus Fn of x minus F capital N of y plus Fn y minus F capital N of y. So this is less than or equal to epsilon over 3. This is less than or equal to epsilon over 3. This is less than or equal to epsilon over 3. So this all is less than or equal to epsilon, and it's less than epsilon, right? So and this holds is just as a triangle inequality applied twice. Yeah, so we have shown that whenever y and x are at distance delta, then indeed we have this a difference less than epsilon as required by the theorem. So this is a very short proof, I would say. Alright, so we have proved one direction of Arcela-Ascoli theorem. Arcela, this is A with apostrophe, Ascoli theorem. Two Italian mathematicians did it over 100 years ago. Well, actually, I know that Arcela generalized the result of Ascoli, and now this kind of a result is very common in functional analysis. So it will come up pretty often in different forms if you learn functional analysis. All right, so now let's do the opposite direction. So the opposite direction is the following. So you have equicontinuity of your family, and moreover you will need that f of n is pointwise bounded. Pointwise bounded means that for any x there exists a function f of x such that the absolute value of f of x is bounded by phi of x for all f in our family. So it just means that, okay, that this bound is specific to x, right? So as there is a priori no uniform bound on the values of our functions. Oh, so alright, so given those two things, they imply that there exists a uniformly convergence subsequence of our family. Alright, so it is one implication, and another implication that I should prove first is that, so this is, let's say, B, and implication A is that Fn is uniformly bounded. Uniformly bounded means that this phi of x actually does not depend upon x. So phi is a universal constant. So in order to show this, okay, so we first show A, right? So we show that Fn is uniformly bounded. Alright. So let us prove that that A holds, right? So let's pick an epsilon greater than 0, and then as our space is compact, there exist finitely many points P1 up to PR such that for any x in X, X lies in a ball. So X, so the distance between X and some of the PI's is less than delta, and the delta is the one that is given by this epsilon, right? In sense of the definition of equicontinuity, right? So this delta. All right. So we have picked up that finitely many balls. So it's a finite cover of X as a finite open cover. All right. So we know that Fn is pointwise bounded. So it means that there exists some constant m such that f of p I is less than m, right? Because, okay, I mean, such m is just the absolute, is the maximum taken over all the finitely many points here. All right, and then we have to compute the absolute bound on the absolute value of f of x. All right, so by the triangle inequality, it is less than f of pi I plus f of x minus f of pi I, and this is less than m from here plus epsilon. All right, so we have shown that m plus epsilon is an absolute bound on the values, or on the absolute values of the values of f of n over the all x, right? Now finally, let us prove B. So, given a equicontinuous pointwise bounded family of functions, we will construct a uniformly convergent subsequence. All right, so again we pick up epsilon greater than 0, we pick up corresponding delta, and so as in accordance with the definition here, right? In accordance with the definition of equicontinuous, of equicontinuity. All right, and then X being compact admits a countable dense subset. Let me remind you that a dense means that every element of X is containing an element of E in any however small open ball around it. So it's like a typical example is it's when X is Rn and E is as a set of vectors with rational coordinates. So it's a typical example of a countable dense subset. Alright, so now we have this countable dense subset, and because Fn is uniformly bounded, it will contain a subsequence that will be uniformly convergent when you restrict to E. You remember this fact we proved in the beginning of the lecture, right? So all right, so there exists a subsequence that is convergent for any X in E. Convergent in the sense that F and K of X is convergent as K goes to infinity, pointwise. All right, so we are going to prove that this particular subsequence is uniformly convergent on the whole X. Alright, so how do we do it? Yeah, first of all, we again select a finite subcover of X with open balls with centers lying in the points belonging to E. Yeah, so there will exist x1 up to xm in E such that X is the union of elements in X lying at the distance less than delta from given from some X S here, right? So we just can suggest application of compactness. So we select a finite subcover from the delta balls around each element of U. We can select finitely many. All right. So then there will exist some capital N such that f and I at xs. So right. So now we want to prove. Uniform convergence for our arbitrary s, for arbitrary x. All right. So now. So now for any xs among those m of them, we can make sure that this inequality holds with here, it's whenever I and j are bigger than or equal to m. Alright? It's just because for each xs this sequence is a Cauchy sequence, right? So it's just a definition of Cauchy sequence. And on the other hand, we know that f of ni of x minus has the same f of ni of xs is less than epsilon as well. And this is again by f by the elements of f and I. Because f and I is uniformly continuous. Alright, so finally we just do the same trick as we did in the proof of this result in the opposite directions. So we need to bound f and I of x minus f and j of x. So this is less than or equal to f and j of x minus f and j of xs plus f and I of x minus f and I of xs plus f and I of xs minus f and j of xs. So this is less than or equal to 3 epsilon. So this is what means that this subsequence is uniformly convergent, because we didn't have any we didn't make any assumptions on x. X was an arbitrary element, of capital X. So this is the proof, and yeah, the next time we will continue to explore properties of sequences of continuous functions. Thank you.